Welcome back, Justin Miller, Roxon College. We are going to keep on pushing and pulling, forcing the issue. So, we want to continue looking at some force. We've gone over Newton's laws of motion, and ultimately we have this, right? The net force acting on an object with mass m produces the acceleration of that mass. A nice vector expression here. Well, what can we do with this? Well, just like any vector, we can represent that vector in multiple dimensions. We're going to stick with 2 dimensions right now, but it always can be generalized to 3. But ultimately, we could do something like this. The net force in the x direction produces the acceleration of the mass in the x direction. And the net force in the y direction produces the acceleration of the mass in the y direction. And we can do it for the z too. What does this really mean? Well, we can break things apart, as we've been doing, into separate dimensions. And we can ultimately always say this: a net force is, well, the sum of the x components, let's do this, the sum of the x in the I hat direction plus the sum of the y in the j hat direction. We can always break open a vector into its individual components, x and y. Or given its x and y components, we can always break it up, or resolve it into its, produce its magnitude and direction via some very fundamental familiar things. So with this, ultimately, you should be able to see that a hat is equal to a sub x I hat plus a sub y j hat. We've already done stuff like that, right? Whether it's varying or not, the acceleration can be broken into its components. So then can be the force broken into its components. And that becomes very useful and necessary at times in order to analyze systems where you have multiple things acting on an object. So some other things that we could do with this, right? Magnitude of force. Say magnitude of a net force. You have the magnitude of sigma f hat is going to be equal to the square root of the sum of the squares of the x and y components. So we can do the square root of sigma f sub x squared plus sigma f sub y, quantity squared. And we can get the direction of the net force. Well, that is going to be equal to theta sub sigma f is going to be, we get it through the arctangent of the sum of the y over the sum of the x components. Sigma f sub y divided by sigma f sub x. There we go. We get a direction of magnitude by knowing what the individual sum of the x and sum of the y components are. Take a look at this. The direction of an object's acceleration is theta sub a is equal to the arctangent of a sub y over a sub x, right? Well, let's come back to this right here and say this is equivalent to looking at the arctangent of, well, the net force in the y direction produces the acceleration in the y direction of the mass, a sub y, and the net force in the x direction produces the acceleration of the mass in the x direction, a sub x. Well, we can write it like that. What's nice about that? Well, this is what's nice about that. M's are relevant because it is a common factor in both of them, and thus we get that the direction of the net force is equivalent to the direction of the acceleration that it produces. So if the net force is in this direction, that must be the direction of the acceleration. I can't have a net force acting on something in one direction, but the acceleration being produced is in a different direction. That would mean there has to be something else affecting its motion. The net force takes into account all the forces acting on the object. So overall, theta sub A must be the same as theta sub sigma F. Because again, it is the net force which is producing the acceleration of the object. All right. So, one other thing we go ahead and do is think about extracting out the x and y components given the magnitude and direction of a force. So, given the magnitude and theta sub sigma F of a net force, we have that the sum of the x components will be equal to the magnitude of the net force times the cosine of theta sub sigma F. And y component of the net force would be equal to the magnitude of the net force multiplied by the sine of a theta sub sigma F. Just like we've done before in resolving vectors in their x and y components. And that's pretty much that. So it's going to be important to be able to use the decomposition or resolution of vectors as well as producing the magnitude and direction. Sometimes we'll have to break things down in order to build them back up when we have multiple forces acting on an object. But overall, Newton's second law kind of spells it out. Net force produces the acceleration of the mass, and if you have forces acting in multiple dimensions, then you can treat them as different directions, different dimensions themselves. And extract them out, put them together. All right, let's do a couple problems involving some Newton's law, and we'll start off with a couple little simple ones. We'll just kind of look at one-dimensional motion, and then we'll get into something that's a little bit more, but not that much. So, here's the problem. All right, so we're going to take ourselves a mass of 0.25 kilograms, and we are going to take it and accelerate it from rest to a velocity of 20 meters per second over a time of 0.47 seconds. So let's just say that there's some ball, mass m. We'll say that it's initially at rest. The initial is equal to 0. And then some force acts on this. And this is some net force acts on it. And over some time, t is equal to 0.47 seconds, this object will now be traveling. V final is equal to 20 meters per second. And let's just go ahead and put I hat in here and try to figure out what is that net force based upon this. So we are also given m is equal to 0.250 kilograms, which actually would be all these added up. 100, 250, take these all together, and I say, I'm going to take this right here, and take it from rest, and over a 0.47 second time interval, I'm going to take it from rest, and I am going to act on it, push it that way in the positive x direction, such that it leaves my hand going at 20 meters per second. All right, so that's that. Was it going exactly 20 meters per second? Probably not. Turned into a brick wall though, no harm done. Didn't come back and hit me luckily. Anyways, this is what we've got. So you think about something physically that we could be doing. How did that happen, right? I took it and I threw it. As it left my hand, that's how fast it's going. We're not asked about what happens afterward. Afterward, it's a projectile. Until it hits the wall, of course. Anyways, we want to figure out what is the net force. Part A. Well, what do we know here? We know by Newton's law, second law, the net force produces the acceleration of the mass. All right, we know what the mass is. Do we know what the acceleration is? Well, we're not told specifically what the acceleration is, but we have a way of determining it. Now, this is where we have to either be told this is a case of constant acceleration, or we would be utilizing an average value. What average force over this time interval would be necessary to produce that change in velocity? So let's just go ahead and assume that this is a constant net force and say that what sigma f hat be constant. Well, if the net force is constant, assuming that the mass remains the same, which is the assumption here, the acceleration must be constant. So that a hat is also constant. Well, if that's the case, we've got constant acceleration, we can utilize equation of motion for constant acceleration to figure out what the acceleration itself is. Because we know that a v initial is equal to 0, a v final is equal to 20 meters per second, and the time interval over which that change occurred was 0.47 seconds. What else is there? There's some delta x and there's some a sub x. We're constraining ourselves to motion in the x direction, so this is kind of one-dimensional constant acceleration. So we know these three things. We want to know what this is. How are we going to get it? We're going to get it through this. V final is equal to axt plus v, we'll put x's there. Vx final is equal to axt plus vx initial. Isolate a, solve for it, subtract vx initial from both sides, divide by t, and we've got ourselves that ax is equal to vx final minus vx initial divided by t, which gives us 20 meters per second minus 0 divided by 0.47 seconds. 20 meters per second divided by 0.47 seconds. I'm going to go ahead and throw an I hat in there because, well, we know that we're working in the I hat direction. And 20 divided by 0.47, which gives us 42.553. Meters per second squared, I hat. So there's the acceleration of this object. Over that 0.47 seconds, it accelerated at the rate of 42.553 meters per second squared. All right, that's great. We got the acceleration now. Once we know the acceleration, we can figure out the force. So we've got that the net force is equal to ma sub x hat. Well, what do we know? We know what a sub x is, and we know what m is. So this is going to be equal to 0.25 kilograms multiplied by 42.553 meters per second squared, I hat, which gives us times 0.25, 10.638. 10.638 units of force, SI, newtons, N, I hat direction. So there is our constant force or average force that acted over this 0.47 second time interval in order to produce the acceleration that ultimately gave us a velocity changing from 0 to 20 meters per second in the I hat direction. Rounded off 10.6 newtons, I hat. What happens if we actually double the mass? You say, oh wait, we don't want to throw something 0.25 kilograms. We want to throw something that's half of a kilogram. I'm not going to do it. I don't want to start breaking bricks or anything. But hey, what's going to happen here? What do you think is going to happen in terms of the force required to produce that same change in motion, but just of something that's more massive? If I take something that's more massive, it should stand to reason that it's going to be harder to make it go from 0 to 20 meters per second over that same amount of time. If it's harder to change its motion, then I'm going to have to use a greater amount of force, right? How much more? Well, part B, if m were to be equal to 0.500 kilograms, sigma f hat is equal to what? So the same scenario here, we'll recall that in computing this acceleration, we didn't care what the mass was. The acceleration was just a function of the change in velocity that occurred over the time interval. So this is still the acceleration. A hat is still going to be 42.553 meters per second squared in the I hat direction if this is what we want it to do. What's not the same is the force, right? Because now the net force is going to be equal to a hat, which is going to be 0.5 kilograms multiplied by 42.553 meters per second squared. I hat, which 21.274. Let's just do this. Enter. 21.276. Sorry, I said 274. Let's say 276. 21.276 newtons I hat. Double this one, right? We double the mass, we double the force necessary to produce the same change in motion over the same time interval. That's it. Quadruple the mass, quadruple the force necessary. So on and so on. All right, so that was a nice little problem involving something fairly straightforward. Let's take something else and do sort of the same thing. Let's say that we've got some object that's initially traveling at 20 meters per second. Now stop it. So here's the problem. All right, so we're going to take some mass, 1,000 kilograms now, and we're going to say this 1,000 kilograms is moving at 20 meters per second in the I-hat direction. And we want it to come to a stop over a distance of 35 meters. What net force is necessary to do that? So how can we model this out? Well, 1,000 kilograms, it can take that being maybe like a little small car. Does it have to be a car? It doesn't, but we can just say some small car. And we've got some V initial is equal to 20 meters per second in the I-hat direction. And this car is going to go ahead and advance itself. Some delta X is equal to 35 meters. And here, the car will change shape a little bit, just a little though, but it'll more importantly be at rest. All right, and what do we want? We want to know what is the net force that produced that change in motion. So one other thing that we need, let's say the mass is 1,000 kilograms. All right, so you slam on your brakes or run into something, I don't know. Let's just say you slam on your brakes. Anyways, some force changes your motion. Let's think about the direction of that force, right? This object's going this way, but it's going to be slowing down over time as it moves forward. What direction is acceleration then? That's right. If the velocity is that way and it's decreasing, the acceleration must be in the opposite direction. So the object is accelerating that way. Well, if the acceleration is that way, that has to be the direction of the net force as well. Well, think about it. If we want this object to go from a higher speed down to a lower speed, something has to be pushing on it in the opposite direction that it's moving. Pushing, pulling, acting on it, we'll say. Exerting a force on it in the opposite direction of its motion. So we should be able to conclude that if we're calling the direction of its motion positive I-hat, the net force is going to be in the negative I-hat direction. And it's important to be able to make those sort of conclusions just by the scenario without computing anything. Have some expectation of what's going to be necessary. All right, so we want to know what the what the net force is. The only thing that we've got to go with is that the net force produces the acceleration of the mass. So again, let's see if we can compute what the acceleration is. We've got a V initial is equal to 0, a V initial is equal to, I'll put initial again, this is final. V initial is 20 meters per second, I-hat. V final is 0, comes to a stop, and it does so in a distance, or displacement, x direction of 35 meters. There's some time interval which that occurs over, and there's some acceleration in the x direction that is necessary for that change in motion to be produced. So ultimately, let's get ourselves the acceleration so that we can figure out what the net force is. All right, so we look at this. Again, working under the pretense of a constant acceleration or average acceleration allows us to utilize the equations of motion for constant acceleration. And one of them says that v final squared is equal to v initial squared plus 2a delta x. We can subscript this all with x. Vx final minus Vx initial, Vx final squared equals Vx initial squared plus 2a sub x delta x. Solve this out for a sub x. Get ourselves that a sub x is equal to Vx final quantity squared minus Vx initial quantity squared divided by 2 delta x. Final 0. We've got then that this is going to be equal to 0 minus the quantity of 20 meters per second squared divided by 2 times 35 meters. So 400 divided by 70, a negative sign out there. And we've got ourselves negative 5.714. Negative 5.714 meters per second squared, I hat. Little I hat out here. That doesn't really matter. We know that it's the x direction, one-dimensional motion, going the I hat, negative I hat. Fantastic. There's the acceleration necessary. So what sort of force was necessary to produce this acceleration? The net force is the mass times the acceleration, which is then 1,000 kilograms multiplied by negative 5.714 meters per second squared. I hat, which is going to be negative 5,114 newtons I hat. 5,714 newtons I hat. So a force acting in the negative x direction produces the object, produces the slowing of the object. And this amount of force over that distance, the object would come to a stop. All right, so I'm gonna do one more little thing with this and just say, hey, what if the initial velocity was only 10 meters per second? Let v initial be equal to 10 meters per second. Sigma f hat would be equal to what then? So we still want it to come to a stop over 35 meters, but it's only going 10 meters per second to begin with. What then? Well, it's the same procedure, right? We've got ourselves a v initial now is equal to 10 meters per second, a v final is equal to 0, delta x is equal to 35 meters. We want to know what the acceleration is so that we can figure out what the net force is. And from before, we've got ourselves that the acceleration will be equal to Vx final squared minus Vx initial squared divided by 2 delta x. So in this case, Vx final is 0, Vx initial is 10, so we've got ourselves negative 100 meters squared per second squared, 0 minus 10 squared, divided by 70 meters. And we got 1.4286, we'll say. Negative 1.4286 meters per second squared I hat. Notice that is not just half of this. It's substantially less because we don't have to change the motion as much. And it's even more than half less than the acceleration necessary to go from 20 to 0 over that distance. So what do we get with this? Well, net force then, in this particular case again, is m a sub x, which is then going to be 1,000 kilograms multiplied by negative 1.4286 meters per second squared I hat, which gives us approximately 1,429 negative sign out in front, newtons I hat. So what was the point with this? Well, the point is we didn't like double the mass or half the mass. We changed the change in velocity and how it's correlated with a particular distance. And well, that is a non-linear relationship there. So what do we get? That's what we get. get something completely different. So sometimes you may think, oh, well, since it's just half the change, we need half the force. That's not necessarily true, right? Depends on whether you're talking about the mass, where that is a constant of proportionality that's linear between acceleration and net force, or a certain change in velocity, which is not linear with respect to a distance. So just beware, calculate stuff out, try to make sense of it. That's it. All right, we'll say that that's it for now. We'll come back and look at another problem, but we'll leave it at that. Be well.